There's always a distinct possibility, I would say. OK, thank you very much. So now we can actually get things going again. Woohoo! All right. So this is the test from last semester. So yours is going to be, it will go over, yep, go ahead. Yes, yep. So we got streaming on again. This is from last semester. And this is, let's see, let me just check the material. Yep, this is the correct one. So this is actually the same as yours, in terms of being exam 2, except your exam 2 would also have double representation in it. So the floating point number stuff, that is going to be in the second exam because we didn't test it in the first exam. All right? OK, so this is the first question. So the first question gives you the following table that shows 2 slices of microcode. So now you have to remember what is microcode, where does it live, what does it do, and so on and so forth. OK? So we'll read the question carefully. After each slice of microcode executes, there are 2 slices, and they are executing in succession. OK? So there are 2 slices that will execute one after another. After each slice of microcode executes, describes any operation performed and the resulting state of the processor. So you have to make sure that you identify all the operations performed. What do I mean by operations? Did we add something? Did we store something into a register? Did we address RAM? Did we read something from RAM? Did we write something to RAM? Which register got updated? And so on and so forth. Okay? So it's asking about those. And you also have to tell me what is the resulting state of the processor after that operation performs. Note any changes to registers or RAM content in your answer, okay, which is something that I just talked about. The only exception to this rule is the microcode pointer, where you do not need to know where it is. Okay? All you need to know is the content of the 2 slices of microcode locations is displayed in the spreadsheet, in the table. The explanation of what happens in the processor is worth most of the points, so describe in details what component does what in each slice of the microcode. Okay, so the nice thing is I have already decoded most, not all, but most of the output of the ROM for you. So everything except for the last or the most significant 2 bits are already decoded into the proper name of the tunnels. So I would assume that you will have a map of the processor, a printout of the processor with you in exam 2. I would also assume that you have a register bank schematic and also an ALU schematic with you in the second exam. If you do not have one, I do not have a spare one for you in the exam. I can tell you that one already. Yes. OK. So are we good so far? Do you guys know what you need to bring just from this discussion? Okay. Now, if you are printing one, you might as well print a few, because you might need to mark up one to answer one question, and then you might need to look at a clean copy for another question. So bring 2 or 3 as spare. Okay. All right. So now we look at this, and we ask the questions. What is the first slice going to do? Okay. So we just go down the list, okay, and try to figure out, what is being turned on, what is being turned off, and what is being done in this entire slice. So I'll give you guys a little bit of time, to kind of think about it. And if you have a map of the processor, it'll be helpful. But even if you do not, we can still figure out a lot of these things without a map of the processor. OK, so let's go down this list from the bottom. Okay, IREN is a 0. IR is the instruction register. So that means we are not updating the instruction register. OK, fine, skip. Go to the next one. RAM cell is a 0. Whew. Because if RAM is selected, then we have a few other questions to ask. In fact, we have 3 additional questions to ask if RAM cell is a 1, which it will become. So we'll explain those 3 questions in the next slides. So we can now forget about RAM load, because if RAM is not selected, RAM load can be either 1 or 0. It doesn't really matter. RIMUX is a 0. RIEN is a 0. So that means no register in the register bank is getting updated. OK. So moving up a little bit, we have RO0 EN being a 1. Register output 0 is enabled. So we are taking register output 0 from the register bank, and we are sending it somewhere, okay? And then the next one is register output 0 cell select is 2. That is the one that selects which register within the register bank becomes register output 0. Okay? 0 is A, 1 is B, so 2 means register C is being used as output of something. Okay? So better jot down some notes before I forget. Okay. So we know that register C in the register bank is output 0 of the register bank. Okay. What else do we know? Register 0 demux is a 1. Now this one I cannot answer because I really do not remember what the processor map looks like. So this is why I said a little bit earlier, it is helpful to have that processor architecture with you during the test. So we open up, and you can use either one. If you already have made printouts before I changed to processor 0003.circ, the old one works just as well, okay, because the meaning of the tunnels have not changed. So we are looking at register output 0 demux, which is this tunnel here. So that tunnel is specifying what value again? Okay, so we go back to here. It is a 1. Okay, so see this one here? So we want to put a 1 into this particular select of this demultiplexer, and that one specifies this wire. So that means we are using the ALU, or it seems like we're using the ALU for something. Does that make sense? Okay. So we go back to our notepad, and we say register C connects to in 1 of the ALU, because that's what the path is establishing. So we go back to the spreadsheet, read some more. Register 1 select, register output 1 select is a 1. Now the select is what is choosing which register inside the register bank that becomes register output 1. So remind me again, what is 2 again? What is the letter corresponding to 2? Register C. Okay, so it looks like we're using register C here again, which is okay. Okay, no, not a problem. So register C in register bank is also output 1 of the register bank. Okay, what else do we need? We also know that register output 1 demux is also a 1. So for this, I have to defer back to the map here because I cannot remember, which one is which one. So we look at this select line here. Oh, sorry, demux. So we look at this demux here, it is a 1. So that means it is going through this multiplexer probably to input 2. Okay, so we better double check and make sure, and we need to look at, this is a 1, and ALUN is going to be a 1, so 1, 1, the output is going to be a 0 in this case. So we are selecting 0, so this is all working out. So we go back here, or we go back to the scratch pad here, and we say register C connects to in 2 of the ALU. Are we doing okay so far? So when you're reading up to this point, you probably should have a few questions in your head already. You're basically thinking ahead of time. It's like, what kind of operation are we performing in the ALU? Because it doesn't make sense for me to make connections to the ALU and it's not using the ALU for any computation, right? So that would be those questions you should be asking, as you think ahead of time. So now we are moving down to this one here. It means the ALU is in fact enabled. Okay, we are using the ALU. And we are using ALU operation number 4. Oh, well, I cannot remember which one is register, which one is operation 4 in the ALU. This is why you also want to print out the schematic of the ALU so that from this picture you can figure out what is operation 4. What is operation 4? Well, you can always count 0, 1, 2, 3, 4. Okay, so 4 is, let's see here. That's our AND gate here. Okay? So we're performing an AND operation in the ALU. I'm going to write it down here. So the ALU performs bitwise AND. Okay. And what is it going to do about the output of the ALU? In other words, the output is going to be presented here, which means in the main processor diagram, it is presented here. So the only thing we can really do about the output is to store it back into the register bank. But we know we are not, because RIEN, or register input enable, is a 0. So we are not doing anything with the result of the AND operation. Okay? So let's see what else the question is giving us as clues. All of the other stuff is turned off. Now this one being a 0 or a 1 doesn't really matter. Why does it not matter? What multiplexer makes use of the address mux? What does it control? Not really. This one controls what drives the address bus to the RAM component. Okay? But because we are not using the RAM component, because RAM cell is a 0, so that automatically makes address mux not really useful. I could have used a 1 here. It wouldn't change a single thing. Okay? PC mux is a 0. Does that matter? I can make it anything. It wouldn't matter at all, because PCEN is a 0. The program counter is disabled. No matter what I do, it cannot be updated. Is that okay? So that's the kind of thing you have to think about is there are key items here that are more important than the other items. So if the key item says a particular component is disabled, there are a few other things that do not really matter anymore. Okay? And last of all, we have bit 24 being a 1. Well, does that really matter to us? Well, bit 24 is the one going back to control the multiplexer here. This is bit 24. And you can see it's bit 24 because it is coming out of the splitter. And the splitter clearly states that this thick light green line is bit 24. So bit 24 is what specifies, are we auto-incrementing or are we decoding from the instruction register? We're just incrementing. So by itself, it's not really that useful. It simply means, yep, when this is all done, move on to the next slides. That's all it's saying. Okay? So when we go back to the scratch pad, where I have written down most of the operations, oh, so this is all I'm doing here. So we are basically doing a bitwise AND register C with register C. But there's one thing that is kind of important. Okay? If you have done the previous homework assignment, you would know the significance of doing this particular operation. What would that be? What would be the significance of doing a bitwise AND? Setting the two flags. There's one is the S flag, the other one is the Z flag. Okay? So, well, we'll just say updating, because we don't know whether they're turning into ones or zeros. Setting kind of implies it's turning into a 1, so updating is more neutral. Okay? Updating the Z and S flags. That is important. So are we good so far with line 6, with this analysis? So now that we know what it's doing, let's apply this to the condition that is given to you. Because when you go back to the question, I give you a precondition. In other words, I'm telling you, okay, right before the first slice executes, this is the state of the processor. We know that the program counter is pointing to location 27. These are all decimal. RAM location 27 has a content of 125, or the binary representation of 125, and so on and so forth. Okay? So what we're doing is we are doing an AND operation of 0 and 0. What is that going to tell you? Okay, but because we know register C is 0, this means we have 0 bitwise and 0, making the sign flag equal to what? Zero. What about the 0 flag? The 0 flag is a 1. Okay, so now if you're asking, why is the sign flag a 0? You have to go into the ALU, find out what is S out, okay, the tunnel S out in the ALU, and say, well, if the result of the operation is a 0, what is the sign flag of that operation, okay? And likewise, you have to say, if the result of the operation is 0, 0, 0, 0, 0, 0, 0 is a binary number, what is going to happen to the Z flag? Because the Z flag is a NOR of all 8 bits of the result of the operation. So you have to figure out those things to come up with the answer that the sign flag is going to be a 0, and then the 0 flag is going to be a 1. Are we OK so far with this part? Now, since this is a review, I can do this a little bit more. So I can right-click on this, go to the ALU. The output of the operation is presented here, okay? So you can see how bit 7 alone, by itself, is connected to S out, or the sign flag. You can also see how all 8 bits are going to this splitter. Now, this splitter looks like it's useless, right? Because I split up everything, and then I seem to be reconnecting everything. But that is not the case. I split up all 8 bits, but they are connecting to different input pins of this particular NOR gate. In other words, I'm performing bit 0, NOR, bit 1, NOR, bit 2, NOR, bit 3, and so on. So this NOR is taking every single bit of these 8 bits and compute the negated OR from those bits. If all of those bits are zeros, then you have the OR having the result of a 0. But because this is a NOR, the 0 becomes a 1. Is that OK? So the schematic should be able to tell you everything. All of the answer that I have just derived, by looking at the schematic, you really should be able to come up with the same answer. If you cannot, that means you may not be understanding the operation of some of the components of the processor. And you might want to ask questions related to that if that is the case, because that's what you'll be tested on with exam 2. Are we good so far? So the practice test is a way for you to kind of find out, how much do you understand, in terms of how the processor operates. Okay, are we still good so far? Okay. So the next part, there's a next part to it, right? So the next slide, sorry, I have to do this. So the next slide is the second column, and when you look at the second column, IREN is still a 0. We are not decoding the instruction register, so we are not just hyper jumping to some other location in ROM. We're continuing. RAM cell is a 1. Now you have to ask a few questions. Okay? If RAM cell is a 1, I would ask 3 additional questions. Okay? The first additional question is, I know we are doing something with RAM. Are we reading or writing? That would be the first question. So RAM load sets is a 1, which means it is a read operation. We are reading the content a location in RAM, but we have to be doing something with it, right? The next question is, where are we reading from RAM? Okay? So which bit here tells you who is driving the address bus? We just talked about it a little bit earlier. Address mux, ADDR mux, okay? So ADDR mux, I'm doing a little bit slightly out of order because those are related. So ADDR mux is here. It is a 1. Okay? So we have to go back to the processor schematic to find out what that means. So when ADDR mux, which is here, is a 1, that means the PC or the program counter is driving the address bus of RAM. Are we good so far? Okay, so in terms of taking down some notes here, this is the second slice, or we'll call this slice 1, and this is slice 0. So in slice 1, we are reading whatever the program counter is pointing to. Okay, I'm just using the C notation here to mean we're dereferencing the program counter. Okay, so the last question, whenever you use RAM, is what are we doing with that data? Who's getting it, right? So now you go back to the question and you ask, what is getting updated? Oh, try to focus on the ones, right? The zeros typically tell you this is disabled, we are not using it, don't pay attention. So focus on the ones and all the non-zeros. So we can see the program and counter enable is a 1. So that means we are about to update the program counter. The question is, how are we updating the program counter? Is that okay? So that's the kind of chain of reasoning I want you guys to also exercise when you read questions like this, okay? So there's no better place to go than to go back to the schematic. Because when you look at program and counter, it says the program counter is about to be updated. Now the question is, who is driving that wire? Well, it's being driven by a multiplexer, which means we have to know how it is choosing which input connects to the output. That is being done by PCMux. But remember, PCMux is not coming from the ROM. PCMux is actually the output of another multiplexer, and that's why the control signal of this multiplexer is called PCMux, because it's a multiplexer that specifies the select line of another multiplexer. Okay? So PCMux does come from ROM. So we go back to the question, and we see that PCMux is a 1. So if PCMux is a 1, that means if we are using this input to connect to this output here. So now the question is, what is this input corresponding to? Well, let's track it down. This is coming from the splitter. The splitter connects to the output of the flags register. The flags register is what is storing all the flags, okay, including the 2 that we just mentioned. So what do you think is bit 1? Or how do you find out what bit 1 is in the flags register? It's the Z flag, right? Now, the way we know it's the Z flag is when you look into the ALU and you go all the way to the bottom, okay, we can see how the carry flag is bit 0, the Z flag is bit 1, the sign flag is bit 2, the O flag, overflow flag, is bit 3, and the L flag is bit 4. That is how we know which bit in the flags register reflects which result in the ALU. Is that okay? So we are looking at the Z flag. The Z flag becomes PCMux. Okay, take note of that. Okay, because remember, I cannot give you any points unless you tell me that you understand how the processor operates. So we can now say that PCMux is really the same thing as the Z flag, but we know from the previous step the Z flag is a 1. Are we good so far with this analysis? Okay. So what does that mean when PCMux is a 1? Well, go back to the schematic, and we track it down. So when PCMux is a 1, that means we are selecting input 1 to update the program counter. So now we have to track down who's controlling this mux here. Well, this mux is controlled by the output of this AND gate. We know PCMux is a 1 already. We know register output 0 enable is a 0. So that means the output of this AND gate is going to be a 1. Okay? So that means input 1 is what is connected to the program counter. We track this down, and guess where that brings us? It brings us to, okay, so let's track it down. It's coming from the D port of RAM. So this is what we are doing with the output of RAM. So when we complete this entire picture, we now say PC is updated by whatever is pointing to. That's the effect of the second slice. But we are not done yet, because we already know what the program counter is pointing to. We know the content of certain locations in RAM in the question. So we go back to the question, we say, okay, the program counter is pointing at location 27. Location 27 has a content of 125. So what we are doing is we are updating the program counter so that now it is going to point to location 125. So to finish the entire question, I have to remember to state that. So the program counter becomes 125. or the binary representation. But you don't have to convert anything into binary because it doesn't really matter whether you write these numbers out as binary numbers or decimal numbers. I just need to know, do you understand how the processor operates? So are we okay so far? Yes? No, kind of? Okay, so we got a few confirmations, we got a few maybe, and I think there might be a few definitely no. Yes?
Line 16 is a jump.
It is jumping, yep.
And then when now jump to location 125?
The result of the jump is the next opcode that we'll be getting is from location 125. So we are in fact branching to location 125. Yep.
Do you have any more examples of this? Or any more slices?
Indeed we do. We have a whole bunch already in the processor itself. So if you right click on this and look at the content, anything that is not a whole bunch of zeros like these guys and these guys, that's kind of what we are looking at. Except it's not nicely decoded, and so you have to kind of decode it into those tunnels. It's not really that difficult, to decode that. Okay, so let me just ask the question, see if you guys know the answer. So we'll just focus on, okay, I'll click on it so that we can focus on that one. So we'll just focus on one location here. Let's pick this one, okay? So we are looking at location 530 in the ROM. This is one slice of microcode. It just doesn't look like one, but it is one, okay? So now my question is, can you break this 7-digit hexadecimal number back into the values of the respective tunnels like the ones in the question? You should be able to, okay? And the question is, but how do we do that? That seems really, really hard. Well, it's a lot of counting because you have to know which bit is where. But other than that, you can just, okay, first of all, how do you do this by hand? Because you cannot program anything you cannot do by hand, right? So we are looking at which location again? 1500B90. 1500B90. Okay. How do we convert this back into binary? Every hexadecimal digit is 4 binary digits. Yes. So, well, the first one you can still use all 4 digits. You just need to truncate it because otherwise you end up with 28 bits instead of 26 bits. Okay. So it becomes 0001 for the 1, 0101 for the 5, 0000 for the 0, 0000 for the 0, 1011 for the B, 1001 for the 9, and then 0000 again for the 0. Okay? So this is your bit 0 here, and this is your bit 25 here. You can figure out the rest, right? So you just have to use the processor architecture thing. And okay, let me close this first. So what the next thing you need to do is to just look at this particular splitter and look at this particular splitter so you know how the bits are split into the various tunnels. Then you can come up with a table just like in the question. Now, once you can do it by hand a few times, okay, my recommendation is to write a program to do it for you. So you just type in the hexadecimal digits and have your program to automatically fill in the values for each respective tunnel. It's a good exercise, okay? If you can program it in C, C++, you can use a spreadsheet to do it. My favorite is using a spreadsheet because it really is doable in a spreadsheet in this case. Or you can just choose to do it by hand a few times. I mean, that's fine too. But that's what I want you guys to do. But this is in response to the question of, do we have more slices to decode? And the answer is yes. The processor itself already has plenty of slices. In fact, the slice that we have just looked at in the question is a combination of 2 slices, or one slightly modified slice and one that is non-modified slice, right? The first slide corresponds to AND CC, with the minor change of RIEN is disabled here. We are not storing the result. Other than that, it is actually the same as AND CC. What about the second slice? What do you think the second slice looks like? It depends on the Z flag, and it jumps to a location based on what the program counter is pointing to. It's the same as your JZI instruction. So look up the JCI slice. It is actually identical to this one. Look up the AND CC slice. It is almost identical to this one. All right. So are there any questions about number 1? No questions? But I'm hoping that you guys are also kind of reminding yourself what to bring to the test. Okay? It's open book, open notes. There's no limitation of what printed or handwritten material you can bring with you. So you would definitely want to have the schematics of the processor, the register bank, and the ALU for sure. Okay? Depending on how well you can do the conversion from base 16 to binary, you may or may not want to have that little table of 16 items. Okay? Some of you probably have already enough experience and you can do it by heart. Others may say, okay, I want to bring that little table with me. That's fine. It's just a little table. It's not really a big thing. It doesn't take up a lot of space on the piece of paper. Is that okay? All right? Okay, so assuming there are no more questions, we move on to number 2. So number 2 is compiling. Okay, so I want you to give me the code corresponding to the following C code. And A, B, C, and D are not just variables. They do correspond to the respective registers. Are we good? Okay. So how would you do this? I mean, what is the process of working on this problem? Removing the brackets, and did we talk about anything about how to remove the brackets and gradually convert this program into an assembly language program? We did. Okay, so you have to do it step by step. Okay, this is not even close to the complexity of the one in the module. The one in the module is a killer. I mean, that one is going to take you a long time. This one is not quite as bad. Okay, so I'm going to work on this one myself here. Okay, first of all, we also have the type of A, B, C, and D, which means we know that we are dealing with signed or unsigned values. I mean, if you just look at how A, B, C, and D are declared, are they signed or not? They are signed. Okay, so it is kind of important to keep that in mind. So the next thing we have to do is to look at the while loop. Okay, I'm going to write it here, and then we'll convert it, right? Okay. I don't even care what is inside the loop, because my first concern is, can I convert this into just a conditional statement and labels? Okay, so what does it convert to? In other words, if I were to comment out these things, how do I implement exactly the same logic, but without using while? Start with a label, right? This is a while loop. You start with while begin. You end with while end. I know you cannot type your program kind of like this, but you can kind of use a notation. I'll show you guys later on how to use a notation to do the same thing. But the key is, at the end of the loop, we always have a jump instruction going back to the beginning. And we also need to look for a reason to get out. What is the reason to get out of the loop? B has to equal to 0. Okay, so we can test register B whether it's 0 or not. But wait, the compare instruction cannot compare against constants, right? So how do I compare B to 0 when I cannot compare to constants? We just do, it relates to the first question. Yes? You cannot just do JZI, because the Z flag still has to be set by one arithmetic operation. See?
Put the 0 in the register.
But all the registers are being used. Yes? And, very good. And register B with B. Does that remind you of the lab on last Thursday, which is due this Thursday? I sure hope so. If not, I have just given you the answer of at least one of the questions of that lab. Okay. So and BB, and then we can use a JCI. Okay, we confirm that B is a 0, then we can get to while end. Now, what label name you choose to use, I don't really care. Okay, if you want to label these things as L0, L1, L2, L3, be my guest. Not a problem. Okay, I just want to make it clear what each label means, so I use meaningful names, in the label with the labels. Okay. So this takes care of the while loop. So now we can focus on the next one, which is A gets A plus D. How do we implement A gets A plus D? Okay, so we can use an add instruction. And in what order should we specify the two registers? A and D. That is correct. Okay, the first operand is the one getting updated. All right, so we got done with that one, and now we have to deal with the conditional statement. If A is greater than or equal to C, we perform a conditional statement. Okay, so how do we translate this? In other words, under what condition am I going to skip this section of code here? What is the reason for me to skip that section of code? When A is less than C. Okay. Oh, less than. I can deal with less than, right? We like less than because we can translate everything down to less than. I hope you guys remember that discussion too. We have a way to translate everything down to just less than. Okay. All right, so that means we have to compare. Okay, this time we're comparing A to C. And then what do I need to do here? J, not S, not JCI. JCI means we're dealing with unsigned values. JLI, okay? So I'm going to be very picky here, because if someone gives me a JSI, even though it does work for some cases, it does not work for all cases. I will only give partial credit if this is a JSI. If this is a JCI, if I can, I would deduct even more points, because a JSI says, that person seems to understand this is a signed compare, just chose the wrong flag, okay, which does not work all the time. But JCI means, that person did not pay attention or did not understand that this is a signed comparison. Okay, so JCI would get the least partial credit, JSI would get some partial credit, JLI would get all the actual credit for this instruction. Any other jump instruction would not get credit. So JOI, no credit. JZI, no credit. Okay? So if you're not understanding what the differences are between those flags, it is time to review the module on binary number comparison, because the flag explanation is in that particular module. Okay? So we'll have this to go to yet another label. We'll call this endif, okay? And endif is over here, which is marking the end of the if statement. Okay, so now that we have the control structure done, how do we compute the difference between A and C and then store the result back into A? How do we do that? Subtraction. And how do I specify the order of the operands? AC. AC is right because A is the one updated, and it is always the first operand that gets updated. Next one. Oh, that looks ugly because I cannot do a subtraction with a constant, cannot do it with an immediate, and yet I have to specify that 1. All the registers are being used, not shift. We can decrement, very good. We can decrement. So we just decrement B, and that's it. We're done. The program is, yep.
Yeah, something like
Yes. Yep, you can unfold that into 3 decrement statements. Yep, correct. So are we good so far with number 2? Yep.
So for flattening the conditional if statement, if it was dealing with signed integers, would we be able to use JSI without it in contrast with signed integers?
If it is unsigned, then you use JCI. Yeah, so this is all stuff in the binary comparison module. It kind of explains why the borrow flag is effective for unsigned comparison, and how the signed flag, in theory, is the one thing that we need for signed comparison, but it cannot get a job done by itself because we can overflow. When we overflow, the signed flag indicates the opposite of what it should be doing. So now we have the signed flag, we have the overflow flag, and then we combine those 2 using exclusive OR to become the L flag. So the L flag is the only correct answer here for signed comparison. Even though JSI comes close, it does not work in all cases. Yep.
What does the AND BB do?
The AND BB, it does a bitwise AND between register B and register B. So what it does is what we just talked about in question number 1. Yep. So you can see how one question can potentially help you understand or answer another question, in the test. That would be kind of interesting from my perspective to design one test where every question is a hint to another question, and it's circular. Question number 3 of 4, okay, so reverse engineer, in parentheses, decompile the following TTP ASM code back into C. Note that your C code needs to resemble the control structure of the TTP ASM code as closely as possible, and not merely just to reproduce the same end effect. Okay, so I want you to turn this back into a structured program, using while, conditional statement, potentially with else, that sort of stuff. So I don't want to see any go-tos. I don't want to see any labels in the C code. I want to see structured code in this case. Okay. So now you can see that I was actually being quite kind to the students because I used indentation, and the correct indentation too. The worst that I can do is not to not use indentation, but to use the wrong indentation. That would be bad. That would be like tricky. But this is like super kind because I'm telling you the nesting of the logic already. Okay? So the way you decode logic like this is always with label definitions and the use of labels. Okay? Those will give you the sense of structure. See how label 1 is defined here? And label 1 is used down here? That means the control structure related to label L1 spans from here to at least here. Is that okay? Look at label 2. Okay, label 2 goes all the way from here to here. And then label 3 is defined here, but is only used here. So that means whatever label 3 is used, that control structure is nested within the control structure of label L2 and L1. So that kind of gives you an idea of the nested nature of this code already. Okay, so how many control structures have we talked about in this class? There are only 3. Conditional statements, if, possibly with an else, while, do. Okay, well, in C, there's no do in the while, but we have a while loop. And we also have a do while loop. Okay, the only difference is pre-checking versus post-checking, right? So now can someone tell me, do we have a loop? What is label 1 corresponding to? What kind of control structure is label 1 corresponding to? Yes? It's a while. Very good. Because the jump is from here back to here, that tells you it is not a conditional statement. Conditional statements only branch forward, not backwards. Any branch that goes backward has to be indicating a loop. But how do we know this is not a do-while loop? It is unconditional. The branch at the end, back to the beginning, is unconditional. That tells you it is a while loop and not a do-while loop. Okay, so if it's a while loop, what is the condition? Okay, so I'll be writing stuff on the side here. Okay, so we have a while loop. So now we focus on the while loop first. Okay, what is the condition of the while loop? In other words, when do we stay in the loop? The assembly code will tell you when we get out of the loop, but in the C code, you have to tell me when you stay in the loop. So remember to invert the logic. The JZI is what is taking us out of the loop, right? Can we see that the JZI here on line 5 is what is taking us out of the loop? So that means we have to understand the reason behind why are we getting out of the loop. We're getting out of the loop when the Z flag is a 1. But who is changing the Z flag? The AND operation, right? I thought we have just seen something like this, didn't we? Exactly. If it equals to, we get out. If it does not equal to, we stay in. Okay, so that means if B does not equal to 0, we stay in the loop. Right? This is a correct answer. It will get 100% of the points allocated to this part of the answer. But guess what? This will do too. Yes? No? Maybe? If you're pondering why B is the same thing as B does not equal to 0, I strongly recommend that you kind of jot down that question and try to answer the question. If you can answer right away, that's good. Okay, that means you know your C and C++ really well. If you're pondering, that means you might have forgotten one key concept of C and C++ that has to do with the fact that C has no Boolean type. Okay, and if somebody is thinking, I don't think this really matters, then I will have to say it does matter. Big deal. Okay. Okay, so that takes care of that. So that means now we can focus on what is inside the loop. So what is inside the loop starts on line 6 of the assembly code, starting with this one, and it ends all the way on line 13. So now we are looking at line 6 down to line 13, and we are trying to figure out what that is doing. Now remember, I want you to give me the C code and not really just a literal translation of the assembly code. So line 6 is loading A with 1. So if you give me something like this, I would say, yeah, I'll give you partial credit, but you're not going to get full credit. Okay? So what am I doing with that A when I LDI A1 between lines 6, 7, and 8? What are those 3 lines doing? We are doing a bitwise AND, right? Because AND as an operation, as an opcode, as a mnemonic, always specifies bitwise AND. So now the question is, what am I bitwise ANDing? Well, we know register A is a constant of 1, so we know 1 is one of the operand of bitwise AND. The other one is C. So I'm performing a bitwise AND between register C and the constant of 1. Yes?
You're getting the
Least significant bit.
yeah, the rightmost bit of C.
Yes, I'm examining the least significant bit of register C. Very good. So that means we have a conditional statement here that says C bitwise AND 1. Okay, now how do I know that it looks like this but not the negated version of that? It has to do with if the bitwise AND results in a 0, I go here. I skip the operation in between. Okay, so that means in C code, I have to flip that logic around and say if C bitwise AND 1 is non-zero, then I'll perform this operation. What is the operation that I'm going to perform? It's line 9. Yep, there's no other way to express that. Okay, it's just D++. Okay, so once we get to line L3, label L3, or after this operation performs, we will be at line 11 in the assembly code. So can someone tell me what is line 11 and 12 doing? We're right shifting by 1 bit. Okay, and store the result back into register. Let's see here. It is stored back into A, I think. It's stored back into C. So C is C right shift by 1 bit. Are we good so far? Okay. And then what am I doing with line 13 of this program? Yep, B is just decremented. That's it. That's the C code. Can we understand the types of registers A, B, and C in this code here? Is there anything here that tells you whether the registers are signed, should be interpreted signed or not? Go ahead.
I agree. I think it should be unsigned because it looks like you're doing like all the, because B looks like the count of C, the count of bits in C, or it would fit the model of B being the count of
Okay.
number of bits in C, and C just being a binary number.
Mm-hmm.
And you're counting how many ones with D. So at least B and D should be unsigned because they're counting number of bits.
Okay. Well, actually, if you look at it, there's no actual clue whether registers B and C. Let me take it back. There's no telling whether registers B and D should be signed or not, because we did not see any JCI instruction which would have pointed out to unsigned. We did not see any JLI which would point to the direction of signed. Yes.
Yeah, shouldn't the shifting give you a clue?
Hmm?
If you're shifting, you're basically trying to use all the bits, right? So
But it doesn't have to be signed. Doesn't have to be unsigned either, right? So we really do not know. Now there's one, but I'm not going to hold you guys accountable. Is the right shift operation does confirm that register C is unsigned. Why? Because when we use the RSH instruction using the right shift operation, it does not replicate the sign bit. And therefore, we know it is not a signed right shift operation. Now, I haven't really talked to you guys about signed extension, so that's why I'm not going to hold you guys accountable. But the idea is we really do not have any clues of the signedness of all of these integers. Yep.
The only way to really get those clues would be if it had JLI or JCI
Yep.
instructions, right? Okay.
Yes, that is correct. So are we good with the answer of question number 3 and the process of getting to the answer? It is more important that you get the process, how we solve the problem, how we connect the pieces, than the actual, detail of the solution. Because the detail, you can always go back to the video and watch it again. Yep.
shouldn't you initialize B and D?
Oh, right. You're right. Okay, so B is 8, and then D is 0. Thank you. And don't forget the semicolons. Yep.
Shouldn't you do like the int 8 underscore t? Because that's what you get.
Yep. So, but since you cannot really tell whether it should be signed or unsigned, then you can say, this A, B, C, D, or unsigned U int. Both we consider correct, because we really cannot tell whether they are signed or not. Question?
You have to initialize a too.
Register A does not need to be initialized, because register A is not really used other than as a temporary register. So it doesn't really, it's not even declared as a variable. Is that okay? So far so good? Okay, so what does the loop actually do? B is initialized to 8, and okay, so this is stuff that is not assembly language related, right? This is the kind of stuff that P300 and P360 should introduce you to. So what does the loop do? Okay, how can we run this thing in our head and understand what it does? Yes?
I was just going to give you the answer, but go ahead, run through.
Okay, so when you look at register B is nothing more than a counter to count how many times should I go through this loop? 8 times. Okay, that's the purpose of register B. Because it's initialized up there, it is compared here, and it's decremented here. Okay, it is just controlling how many times should we go through the loop. 8 times. Okay, cool. What about register C? Register C is not initialized. Register C has some kind of value. Okay, it's not initialized, up here. But what we are counting is each iteration looks at bit 0 and says, if bit 0 is a 1, I'm going to increment register D, which was initialized to 0. Otherwise, we don't do a single thing. Okay? But then we say, oh, wait, we're going to do a right shift on register C. In other words, as far as register C is concerned, bit 1 now becomes bit 0, bit 2 becomes bit 1, bit 3 becomes bit 2, and so on. So in the next iteration, it'll be examining another bit. Even though we're looking at bit 0 again, that so-called bit 0 really is another bit in the original register. So what we are doing is we are counting the number of bits in register C that are 1s. That's what this loop is actually doing. So that reminds me, this time when I ask a question like that, I can give you actual values of C and ask you, so assuming this is the value of C, what is the value of D after this loop completes? Then you have to actually run that code in your head. Okay, question number 4. Fill in the underscores in the following code to attempt to execute each no-op instruction exactly once, assuming execution starts on the first line of code, which is line 1, and it ends at the halt instruction, okay, which is down there somewhere. If it is not possible to reach a particular no-op instruction, explain why that is the case. Okay, so the entire program is a little bit long like that, okay, and here's a bunch of underscores, and your job is supposed to fill in these underscores. So the question is, which no-op instruction can we reach and which one can we not reach? So now you have to look at the overall code. Does it resemble something that you have seen? I certainly hope so, because you just saw something like this on last Thursday. So we are comparing bytes to the byte that is next to it. Okay? And based on that comparison, so based on the comparison of B, which is the reference from A, and based on B versus C, which is the next byte, we are just executing a sequence of conditional branches. And I'm asking you, how do you initialize all those underscores so that we can hit as many of these conditional branches as possible? And there will be some that is impossible to get. And then you have to identify which one is impossible and explain to me why it is not possible. Okay. We got 1 minute left. I think we got enough time to do it. JCI happens when 2 bytes are the same. So you just need to have 2 bytes that are consecutive next to each other, and they have the same byte value. Easy peasy, right? Darn it. Just ran out of time. JCI is unsigned comparison, confirming that the first number is less than the second number. Can we do that? Yes. Okay. I have just a whole bunch of notifications queued up. Okay. Now, what about JSI? Gets a little tricky, because to get to the JSI, it means JCI cannot happen first. So you're looking for something where the unsigned comparison says not less than, but the signed comparison says yes less than. Okay? But you can make it happen. Okay? It is still possible. So now we have a JLI, but in order to get to this JLI, we have to make sure that JZI did not happen, easy peasy. JCI does not happen, kind of easy. JSI also does not happen. So now we know that the sign flag is a 0, but you want the L flag to be a 1, which means you're forcing the O flag to be a 1. Okay? So you have to look for a case such that the L flag is 1, O flag is 1, sign flag is a 0, C flag is also a 0. Okay? So you're putting more, I'm putting more and more constraints to get to the later ones. Okay? JOI should be impossible to get to. So JOI is definitely impossible, but for all of the other 4 conditional branches, you have to, it gets successively more difficult to figure out, because to get to each one, you have to make sure that the earlier conditional branches do not occur. So you have to think of a sequence of bytes that you specify later on, so that you can arrange for that to kind of go through. All right? Yep.
In line 3, you're loading the value at byte 10 into B.
Uh-huh.
But does that mean that you then have to count up how many bytes are in this program and see what?
No, you do not. So we just have to make sure that there are enough spots here. So you can see that we have how many pairs of bytes. We got, this is for the first iteration, second iteration, third iteration, fourth iteration, fifth iteration. So we do have 10 bytes, right, which is good for 5 iterations. And I only have 5 conditional branches. So in theory, we have enough bytes to go through every single conditional branch, except that at least one conditional branch cannot happen because of the structure of the conditional branches. Yep. So if you put 0, 0 here, that takes care of the Z, right? And then you put, now, the next one you have to be careful, because you only want to trigger the C flag to happen, but not the sign flag. So how do you make sure that the C flag is triggered, but the sign flag is not triggered? The C flag is a borrow flag, so we want to end up with a borrow, but we want the sign flag to be a 0, 2. Okay, so, a 1 and a 2 would do, okay? So if you put a 1 here and a 2 here, it's going to work. Because 1 minus 2 is going to set the borrow flag, and here we go. We take the JCI. The next 2 instruction, or the next 2 bytes, is going to be tricky, because we need the borrow flag to be cleared, but we want the sign flag to be set. So how do we make the borrow flag cleared, but the sign flag is not cleared? Just give me one quick example. Just between -1 and 0. How do we order that subtraction? 1, 1, 1, 1, 1, 1, 1, 1 minus 0 would end up with the borrow flag being cleared, but the sign flag being set. Does that make sense? So that means we can have 255 and a 0 here, so that the JSI can happen. Is that okay? What about the JLI? Okay, so this is where I need a piece of paper too, because I need to track that. So at this point, we want the carry flag to be a 0. We want the sign flag to be a 0, but we want the L flag to be a 1. Okay? Now, it's not really that important, but we want the Z flag to be a 0 too. Okay, so how do we make that happen? Come on. Come on. Okay, first thing. Okay, when you encounter a question like this, what are you going to do? You look up. What do you look up? Not past exams. You look up the definitions, right? So you look up the definitions of the L flag first. The L flag is the sign flag exclusive or with the overflow flag. Okay. But we already know at this point the sign flag has to be a 0. Okay? So what is that going to force you? It forces you to say that the O flag is a 1. Okay, very good. So if the O flag is a 1 after a subtraction, what are the two possibilities? Remember the minuend, the subtrahend, and the difference. So if the minuend is negative, the subtrahend is non-negative, the difference should be negative, right? Because we are subtracting a non-negative thing from a negative thing, so the result should be negative. But if it is also non-negative, then we have a problem. And then we have that, right? Do you remember this equation? What if you say, darn it, I forgot about the overflow flag equation. What am I going to do? What do you think you should be doing? There's absolutely no need to panic because you brought along with you the schematic of the ALU. Right? So you look at the schematic of the ALU and you say, oh, how do we define the overflow flag for subtraction? Subtraction is operation 1. This is how we determine that. Okay? So if you understand the concepts, or you understand what the ALU is doing, then you can actually say, oh, okay, I can just borrow from this picture and understand how the overflow flag operates, right? So getting back to the overflow flag. Okay, so we know that the overflow flag needs to be a 1. So we know this entire thing has to be a 1. But we also know the sign flag is a 0. The sign flag is the sign of the difference. So that is a 0. So that means we can throw this one out. Okay? This one cannot be the case. Okay, throw that out. So this is the only case we have left. The difference has the sign flag being a 0. The subtrahend has the sign flag being a 0. The minuend has the sign flag being a 1. Okay? But we also have to make sure that this does not trigger any one of these other cases. So the carry flag, wait, it is clear. Yep, okay. So the carry flag has to be a 0. So how can we make this happen? Okay, what kind of bit pattern are we looking at? The minuend has the most significant bit being a 1. The rest, I don't really know. Okay, 1. The subtrahend has the most significant being a 0. The rest, I don't really know. And then the difference also has the most significant bit being a 0. The rest, I also do not really know. So what can I fill in with the rest to make this happen? Come on, you guys know the answer? Because we know after the first partial subtraction, what is going to be after the first partial subtraction? We know this one is going to be a 1 after the first partial subtraction. So the only way to make the actual difference being a 0 is we need a 1 here too. And how do we make sure there's a 1 here? Well, we just need to make sure that there's a 0 minus 1 here. What about the rest of the bits? Don't care. They can all be 0s. They can all be 1s. But this will make that happen. This will make that condition happen. So what you need to do is just to say, well, we'll fill in all the rest with 0s, convert everything back into decimal, put that into the blank space. We're done. But do you see the process of doing this? You look up the definition first. You have to first understand what is the meaning of that flag. Okay? Then you use reasoning to help guide your answer. Because, do you see how I kind of narrow down the flags? So I know certain flags have to be a 0, certain flags have to be a 1. The result of a certain formula has to be a 1. And because that formula is an OR, we know one side has to be a 0, so the other side has to be a 1. And if that side is a 1, that locks down what we really need, because when we get down to this conjunction being a 1, that really locks down all the bits. Because in order for an entire conjunction to be a 1, that means each individual component of the conjunction has to be a 1. That locks down all the most significant bits. Now we just have to figure out how do we make this one happen. And that one, you have to rely on what you learned in binary subtraction. A 0 minus 1 makes a borrow. So is that okay? All right. So because we talked about this instead of new material, so I'm not going to give you a new lab tonight. So tonight, we'll just be working on the same lab as last Thursday if you are not done with that one. If you're already done with that one, you can ask more questions about the practice exam, or you can go home, have a nice dinner.